This is the third and possibly last of the Class I kinematic problems that I'm going to solve for you. The reason I don't want to do many more than this is very quickly you run out of original ways to make these problems. That is, they all look kind of alike. My pictures are kind of alike. The only thing that can vary is what we don't know, and that throws a little bit of a wrench in the works, but really not much. So anyway, here's one I thought of. Actually, there was one in a book that I use, and I kind of had to beat up on it a little bit, but here are the details. An astronaut finds himself on another planet where the gravity is different than on Earth. He throws a rock horizontally with a speed of 6.95 meters per second. The rock falls through a vertical distance of 1.4 meters and lands a distance of 8.75 meters from the astronaut. That's a horizontal distance. What is the acceleration of gravity on this planet? Okay, so it's we've got a parabolic trajectory there dotted in red. We want to know, let's see, we are given the blue question here, the blue arrow. We're given that it's 8.75 meters from the astronaut, and we know the green one, that is 1.4 meters. We're asked what the acceleration is. Well, without knowing anything else, I wouldn't know how to solve this. So my first step, and should be your first step too, is let's fill out the kinematic chart. We are given delta D vertically. It is 1.4 meters. We are given horizontal distance of 8.75 meters. We are not told what the time it takes is. Vertically, it's going to have 0 starting velocity because he threw it horizontally. Horizontally, it has a starting velocity of 6.95 meters per second. Let me say that acceleration is what we want to know. Just one second, I'll get that looking like it should. And even though this is another planet, what is still going to be true is gravity is going to work straight up and down. It is not going to work sideways. So gravity here, it's hard to video and type, sorry, is going to be 0, and we're going to choose to, well, we don't even really get a choice in the matter. We have to ignore velocity later in both cases. So let me get that symbol up here. There we go. And also here. All right, so we're now officially ready to start. This is everything that was given to us in the problem. If you have difficulty following that, please back up and do it again. But the first step, the single most important step, is getting the information in your chart correctly. It's important for lots of reasons, not the least of which, on a test, if you get the problem wrong but you get the chart right, you get some sympathy points. Okay, vertically, I know two things. Whoops, didn't highlight that one. Two things. Horizontally, I know delta D, Vs, and A. I know 3 things here, so I can solve for time. Once I know time, I will know 3 things vertically, and I can solve for acceleration. All right, that's fairly straightforward. Look, once again, we need Violet. We will use her quite frequently during these two-dimensional problems, much more than any of the other formulas. All right, there we go. Let me give us a little running room here. We're doing this horizontally, which means this second term, because that A is 0 horizontally, it means it goes away. It's always a blessing when that happens. That's what we have left over, and we know, we have to solve for this. We need to get delta T by itself, and that is this. Let's solve for T. There's a video that explains how to solve these if you're having any trouble with that. And now we just simply substitute in our numbers. There's the numbers substituted in, and when I do that math, I get that it comes out to 1.26 seconds is the amount of time it takes for the rock to hit the ground. All right, let's write that in here. Now let's solve the vertical part, because knowing time, we now know 3 things vertically. So we will, just like we did with horizontal, we'll end up using Violet. This time, the first term will end up being 0. So substituting, we get that as our number. And then when we work it out, 2 times 1.4 divided by 1.26 squared. Don't forget to square the number and, of course, the units there in the denominator, but it ends up working out, which when you plug it into your calculator, leads you to an answer of 1.76 meters per second squared. That's not too terribly far off from what it is on the moon. The moon is 1.62 meters per second squared. So this is a planet that is has just a little less mass than our moon does. Actually, there's several variables. It has to do with the atomic makeup, the mass, and the size. But that'll be something we'll get to in the next unit, as a matter of fact. So there's what will probably be the last one. I'll look and see if I can find any more exciting. But I hope that taught you what you need to know. Thanks.